It's okay? Okay. Okay. So this presentation is about cpuidle. Um, Louder? Do you hear me? Okay. Okay. So this presentation is about trying to predict the next event on the system. So it took some time to identify the sources of misprediction, and this presentation has some overlap with Raphael presentation we did yesterday. So first of all, I will introduce the energy aspect of the idle states, their characteristics, and what we call the break-even. After that, we will explain what is really the sleep duration for a CPU, and we will describe the different sources of wake-up of the CPU, making the CPU to exit the sleep mode. From there, we will analyze the governor we have today in the kernel, which is the menu governor. Now there is a new one called the TO governor based on timers, and we will do some analysis of what's happening with this governor, and then we will explain what we can do to improve the situation. So in the during the runtime, we have a lot of activity on the system, and depending of the kind of the activity, we have more or less energy drain on the battery. But we are not interested in saving, in the context of cpuidle, we are not interested in saving energy on this part, but more when we are going idle. So these peaks are resulting of small activities and also bad prediction of cpuidle. So instead of having a flat line, we have a lot of activities because of the different wake-ups and because of misprediction of the cpuidle governor. So how do we compute? So when do we lose energy? We lose energy when we enter an idle state, and the consumption to enter this idle state is we don't stay long enough in the idle state to compensate the energy to enter this state. And so there is a duration we call the target residency. But it's not simple as that. It's also related to the previous idle state. So in this figure, we have here we have a line, which is the energy consumption, so it's cumulative. And here we have the time. Here we are runtime. Then when we reach the idle moment, we have the choice between one state or the other state. If we choose shallow idle state, the cost to enter is smaller, so the slope is less, well, it's more flat. Huh? So steep. Yeah. And then the energy consumption at this idle state is a bit higher. If we choose the other idle state, so the energy to enter this state is higher, but then we save more energy. So the trade-off, the best trade-off is when we reach this point where these two lines cross. This is where we begin to save energy by choosing this deeper idle state. Otherwise, this one is better. So in order to compute this duration, we use a simple formula, which is the energy to enter the idle state, the new idle state minus the energy to enter the previous idle state, and then we do a ratio with the power of each idle state. These values are very hard to get from the stock vendors. So, yeah. No, it's the theory. It's more.
That other concept also applies to x86.
Yes. For the moment, this is the theory are around idle states. So, well, if you are interested on the mathematical demonstration, you have in this wiki page, you have the mathematical demonstration of this formula. Otherwise, if you are interested in trying to find out the target residency, the exit latency, the different characteristics of the idle state, Vincent did give a presentation about the methodology, by measuring the SOC, and we are able to find the target residency for the different idle state. But it's a very long testing. I think it's two days runs before having some result. But well, you have to do that just one time. So all the rest on the system in the kernel relies on this value: the target residency, the exit latency, and also the power state could be a useful information if we can explain, well, if we can give values with a good meaning.
Sorry if I interrupt you again.
Yeah.
Regarding this, the first plot that you show where you are C0, then you go idle in one state and then idle in another state. Does this always happen? Do you always have this pair of transition, like not idle somewhere else, and then back, or
No. You're showing two different choices. The break, like the neither of them are at the same slope as the original state. You can think of it as like, pretend one C1, one C2.
Okay.
So actually, it's all about this target residency. Okay, so that this figure explains how we compute this target residency. Okay. And this target residency is the duration you have to stay idle in this idle state.
Yeah, of course, but you said it depends on the previous idle
Yes,
state.
yes, it's not. See here.
Okay. Oh, of course. Yeah.
So until you are here.
In your list, previous
Yeah.
in your list.
In your list, yes.
The most. Okay. Sorry.
So yeah, so the idle states, we need all these values to be efficient inside the kernel to take the right decision. Because if we take wrong decision, for example, we go idle for a long time, but we choose a shallow idle state, we'll be consuming a lot of energy. If we are always having small duration of idle state, then if we choose a deep idle state, we will be consuming a lot of energy and drop performances. So these values are very important. And today, as Raphael explained yesterday, these values are somehow not very accurate because that will depend on the OPP, that will depend on the configuration of the other CPUs. If we choose a cluster idle state, we won't enter this idle state, but CPU idle state. So what that means, when we exit, the exit latency will be lesser than the cluster idle state, and so on. So it's very difficult to measure and get feedbacks, but we have to live with that today. So when we want to choose the idle state, well, we have obviously to take a decision about which idle state, and in order to take the decision, we have to do some analysis on the past events in order to do some prediction about the future. And we have the constraint because we are in the kernel. The algorithm to do this prediction must be very simple and very light. So we don't have to consume a lot of energy to compute the next event. So this is an explanation, illustration of what are the sleep duration. So in this figure, we can have different situation. we can enter idle, and then we are wake up by a rescheduling. That means that the idle task need to reschedule and give its seat to another task. Or we can be wake up by an interrupt, which can be a timer, but also an interrupt coming from a device. We do some processing, and then we go idle again. So we don't exit the idle task. So we actually have different kind of sleep duration, because some are related to sporadic events on the system waking you up and then you go idle again, or then you have a rescheduling making this idle task to exit. So when we measure the sleep duration, we just measure when we enter idle and when we exit idle. That's the only metric we have. And the result is this metric just give us the duration of the sleep duration, but we don't have any clue about the reason why we wake up. That could be a timer, and that could be the scheduler. And if we try to predict all these signals at the same time, the result is just we have random signals, and we try to get some guess on the feature based on these events. If we try to predict the rescheduling stuff, do we want to predict the scheduler behavior? No. Does it make sense to try to predict the timer? No, because we already have the information. So that approach works only if we have something periodic. If we are lucky between the rescheduling, between the interrupt and the timer, and we have something more or less periodic, then we can do some kind of good decision. But we are lucky. So let's do some experiment. In order to compare, we will write different governors. We have a random governor. So this governor is just picking an idle state, one of the available idle state randomly. We have the modulo governor. So actually the menu governor is taking the decision from the menu governor. It does +1 modulo the number of state, of course. So that means this governor is always doing a decision which is different from the menu governor. Then we have the deepest governor. We don't care about any prediction. We just go to the deepest idle state. And then we have the shallowest governor, and we choose the shallowest state without doing any prediction. And these are the results. So we see that, so it's normalized. So the count, higher is better, and the other ones, lower is better. And we see, for example, for the menu governor, in terms of consumption, we are a bit less than the menu governor. And in terms of frame duration and count, well, count is a bit less, and frame duration is almost the same. But if we have the shallowest state, we have much better count. The frame duration is very small compared to the menu governor, and just for 8% more energy, which is not really acceptable for mobile, but for, let's say, server, it's interesting. So yeah, that's another test, but the number disappear. But well, anyway, so it's more or less the same scheme. Now we have multimedia with audio. Actually, random, modulo, and shallowest perform better than the menu governor. And if we do, and of course, if we have the deepest, we drop. We don't drop frame, but we consume a lot of more energy. And for video, they are the same. And if we choose shallowest, we consume almost 8% less energy than the other governors. So, what is going on with that, with these governors? So here is the menu governor. So what we see is here is always mispredicting compared to the shallowest state. So that's for giant bench, and for example, if we pick this one, it's the audio player. What's happening here is the menu governor is choosing a deep idle state. Then it exits. Because the exit latency is so high that when you do the sum between the exit latency, so we don't have this delta t Raphael was talking about yesterday. We have the entire target residency. Then the next time it is trying to do a prediction, the governor thinks that he has been sleeping a lot, but actually he didn't sleep a lot. So he's choosing again a deep idle state. Yeah. Yeah.
Period, okay? And you were woken up by the tick,
Mhm.
being that you mispredicted. Then the governor assumes that you could sleep, as much time as the next timer allowed you, and that's what was in effect probably here, because it thought it would wake up earlier, then it set a tick to wake it up, or didn't turn the tick off, basically. That it woken it up, and then it thought, oh, I could have slept, for
Longer. Yeah.
and then it, and it takes that into account
Okay.
in the statistics and everything
Okay.
next time. So yeah, so that's why it can be aggressive.
But I think it should be a mix also with the exit latency, because we have exit latency, it's almost 2 milliseconds, so it's a lot compared to the target residency.
Yeah. Okay. But
In our case, the exit latency of the deepest C state is longer than the target residency of the previous C state. So you're in this situation where you can think that you have sleep for 2 milliseconds or
oh, I
3
see. So
milliseconds, and you say, okay.
the exit latency is so long that the measurement is actually very precise. Yeah.
Yeah.
Okay. That
You said milliseconds, right?
Yeah.
Wow.
3 seconds. Yeah.
Because on x86 it's microseconds.
Oh yeah, it's microseconds,
Okay.
but if you think about like packet C, then that would be in a millisecond range.
Okay. The very, very deep one, okay.
Right, but not, yeah.
So the conclusion with this observation between menu governor and WFI is the menu governor is doing a lot of misprediction, and the result is when we are in WFI, the tasks are just doing race to idle, they are packed, and we don't have any latency added by the idle states. So what we have is when we measure the timing, when we have been sleeping, we measure here. So that could be any kind of sources here. So we don't really know what is the origin of the wake up. So if we try to analyze this group, and this group, we have this, well, the first group, the devices, we have this kind of behavior. So if we observe the SSD, so we have on the left, these are the measurement of the interval for the interrupt. So we measure the different, when we have a burst of activity on a device, we measure the duration of the interrupt. And on the SSD, for example, we see on the left, it's the measurement of the between two interrupts. So we see we have some kind of random activity here, and then it's very stable. The graph on the right is the density. That means it represents the occurrences of the same interval. So when we have peaks, that means we have regular interval coming here. Around these values, we have regular intervals. For the network, we see that we have something more or less the same. We have peaks here. If we have something which is without peak, that means it's random.
The only conclusion we can draw is that it happened more often.
Yes.
Than the other
Yes.
intervals, but it doesn't necessarily
No. Yes.
give us
That
more
could. That should be another metric to say, okay, it's coming in a regular. I agree. For the graphics, we have something very random. But that's not really. I don't think that's a problem, because stock vendors wants to put in their driver an API telling, okay, I will finish at this moment my work. That's something they want to add. So this random, we can make it disappear if they can provide this kind of API. And for the console, it's very stable. If we do some analysis on the idle task rescheduling, it's random. It's a random signal. There is nothing we can do. And if we analyze the timers, obviously, they happen, well, right after the deadline, but it's very close to the reality. So we see that most of the devices have periodic interrupts, and the idle task is random, and the timers, well, give an accurate information of the next event. A side note is on the mobile, usually the interrupts are paid on CPU 0. That means the other CPU doesn't have any other source of wake up than timers and rescheduling. So instead of trying to predict the mix of all the signals, we try to identify each signal separately and predict for each signal, which is smaller. And then when we have the deadline for each signals, we can say, okay, the first event will happen at this moment. So instead of doing the prediction here, we do the prediction at this level. So in order to do that, we have to, every time we have an interrupt, we have to store the interrupt number, the timestamp associated to the interrupt in a buffer. And then when it's the system is running, every time we have an interrupt, we store that in a circular buffer. And when we go to idle, that's the different step. I will develop this step after. Let's give the lines of the algorithm. So when we go to idle, we take the interrupt history. We create different table for each interrupt. We reduce the interval number in a log2 basis. We compute an exponential moving average with the values. We put that in another array. And when we find a pattern, we look for a pattern, when you find it, we use then the array of the exponential moving average to get the value for this interval where we have the average. So at runtime, we have one entry point to read the interrupt number and the timestamp. Then we record. So we encode this value on a 64 bits basis. So we don't need more than 48 bits for the timestamp. and we encode the IRQ. So we have just this tuple is stored in a single 64 bits variable in a circular buffer. So that means the more recent event will overwrite the old event, the oldest event. And when we reach the idle time, we have to do things in different steps. So the first thing is, as we have in this interval, we can have different, we have a lot of different values. We have to group them inside intervals using the log2 basis. So it's like the timers actually. The more we have, the higher is the interval, the longer is the interval, and the more acceptable is the error margin on this interval.
So the error grows exponentially from one bucket to the next one. Why would you say the error margin is?
Because it dominates the residency, the active residency. It dominates the active time.
Because dominates the
So you can just go to the deep sea state and get that.
Okay. So also the advantage is the log2. We have an assembly instruction, so it's a very fast. Okay.
Okay.
Yeah. So this is on the left. We have the circular buffer. We have the interrupt number, and then we have the timestamp. So if we take here at idle time, then we flush this table, we read, and we dispatch per interrupt basis on the different tables. So we have an interrupt 31 for all the interrupt 31, and then we compute the interval between two events. We compute the log2 of this interval, and then we store the result in an array. That means this array has, instead of having 0 to 1,000, 1 million microsecond, he has 0 to 32 values.
So the index is interval, right?
It's sorry.
It's not the index. It's just each entry is a log2 delta.
That will be index actually. That will be it's log2, but that result to be indexed on another table.
Stores the number of occurrences. It's my understanding, right?
No. What you have is you fill this table, which is also a circular buffer. Okay.
Yeah. Okay. Yeah.
And
That's easy.
you put just log2 here numbers. So it's first you reduce the size of the sampling. Okay. You don't try to predict on.
Okay, but I was asking about what's the index of the table, to the table. How do you choose the?
Where is zero?
Yeah.
Where is zero?
It's another
Yeah, that's what I'm saying. It's just
it's
there is
a
no
number,
entry. Each
okay.
entry is just a delta.
So now when we compute the log2 of this value, we lose the these values. Okay. So we don't want to lose these values. So in addition, we use the exponential moving average. So this exponential moving average, it's a mechanism used for trading on a low pass filter to track signals. And the advantages of the exponential moving average is it's very fast to compute. And we can tune with the factors called alpha. We can tune the behavior of the signal, so we can make it more reactive or not to the signals.
I can see that it's very convenient to compute, but so for example, if you have Gaussian distributed noise, you wouldn't. It will give you slightly wrong values. Is that acceptable, or do you have any data, or if you try with other averaging functions?
You mean sorry?
If you have for the
which averaging function is good. It depends on the kind of noise that you have.
Yeah,
Right?
yeah.
So if you have Gaussian distributed, what you would want another arithmetic average instead, which is more expensive to compute, but gives you better results.
Yeah.
So do you have any?
No, right now, no. Then, when at the after storing this value, this log2 give an index on another array, and we compute at this index, we compute an exponential moving average of all the values entering in this index. Yes. Yes, we compute. Yes, for every interval falling on the same for every values falling in the same interval, we compute the average. So exponential moving average. So here, for this value, if we have 98, 104, whatever, they fall always on the log2 falls always. It's always 6, and because it's 6, we have the index 6 here in the table, and we compute the average, exponential moving average, on this for this interval.
So if your IRQ is not terminating between having
So if
these are not exponentially combined in
no,
this.
no, because
these
you
are
will
not
have a
right,
log.
They fall in different bits.
Yes, exactly.
Okay, great. Thanks.
Then we introduce another structure, which is the array suffix. So it's this data type is used for compression, analysis of text, finding, and because we have now a table having a suite of numbers between 0 and 32, we will use this table to build the array suffix. So we have here the history of past event. Okay, here. So in this table we have a list of intervals. These are real values actually. It's coming from I think it's MMC. And the computation on log2 is the result is that, okay? We see that we have a period. Its periodic is 5. It's repeating here, and we took a bit arbitrarily the value. If we find a repetition 3 times, then we assume it's if 3 times the maximum period, then we assume it's repeating, and then we can find the next event. So in this example, we have another set of intervals. We compute log2 here, and from there we compute per period. So in the code, we choose maximum period is 5, and minimum period is 2. And then we try to find for periodically if this period fits every time in the array, in the buffer. So that's the mapping. So you see that for a period 5, the repeating is breaking right here. And for the period 4, it's repeating. And then we have a part here. So we can say that here, because it's period 4, we have the initial period and the initial suffix. We know that the 4th element is 2 here. So we can find this by using just modulo by the length of the by the period. I mean, we take the length of the last pattern length, and we use modulo the period, and we have the index in this suffix, so it's 3. 0, 1, 2, 3 is this one. So we find 2 here. With these two, we use the number 2, this index, and we go into the exponential moving average table, and we get the average at this slot. So for this, we created a specific governor called the embedded cpuidle governor, and we clearly identify 3 sources of wake-ups. Rescheduling, which is we cannot do anything for the moment. Its next step is taking care of that, and would like to think with you about the workload you have, because I think we can identify some kind of workload and find the situation. We have the timers, and then we have the interrupt prediction there. So of course the question is the selection process, the prediction computation, does it have a cost? Yes, it has a cost. This code is not yet optimized. What we have here is the for different OPP on different CPUs. So we see that it's almost well, it's cannot say the double, but yeah, it's significantly bigger, but it's not. It does not explode in terms of computation. However, because of mobile, all the interrupts are pinned on CPU 0. That means this computation we have for the menu governor happens on every CPU, while by using the interrupt next prediction, it just happens on CPU 0, because on other CPU, because there is no interrupt, we just skip that. So the increase of the computation here is largely compensated by the saving on the other CPUs. So yeah, so also if we have so we have a bit more computation, but also we have to leverage that with the situation. If we have a lot of interrupt, of course we take more time to compute, but if we have a lot of interrupt, that means also there is a lot of activity. So do we really want to go deep idle state and just choose based on the rate of the interrupt, just choose a shallow state instead of going to try to predict something complex? We can do some kind of shortcut and make the things more efficient. So these are the results for the test. So I compare that with the menu governor again, which is leverage, and we have more or less for this test 23% more performances in terms of count, and the duration of the frame is reduced by 35%, just for almost 1.8% of more energy. For the other test, it's something similar. We have a better energy for better performances, and that's for the exoplayer. So the result is 97, so 3 and more or less 4% of energy saving. So what we saw, that is we've previously, when we tried to compare the different governor by creating one doing shallow state, we saw that there is, I don't know if I can go up. No, yeah, here. So for the exoplayer audio, so we are more or less the same than the shallow state. But for the video, we see that we have 92. So we know it's possible to do better. So that's the next step, trying to identify. The idea with by adding this specific governor is to try to stick to mobile profile instead of server, because if we use a common governor between server and mobile, every time we will try to save energy, we can have a drop of performances on server side. So it will be very difficult to find a good trade-off between server and energy. So the reason of writing this simple governor by identifying each sources, we can find the weaknesses of the prediction, where is coming from the bad prediction, and identify the different workloads in order to optimize this governor specifically for mobile.
What is very good for your active use cases and it really does whatever were the gaps, right? What about when our system transitions from an active phase to an idle phase? So suppose you're running something, a game or something, and then that ends, and then suddenly you have an opportunity to sleep at the deeper state, right? So how does this compare with the menu governor over there? Because using an EMA will mean that you will require a little more time to decay. So basically you will enter the deepest state a little later than using an ordinary menu governor. That's at least how it would suggest. Do you have any data regarding that? So
that's the third part of the this governor, which is not yet. We have to investigate with the workload, identify some kind of workload, and say, okay, we are in this situation, so choose this state, or choose this state.
When you stop seeing interrupts from a source, do you generate fake high latency events in your table? How do you make the table decay when you're not seeing?
I'm sorry.
So suppose you stop seeing interrupts for IRQ31. Your rotating tables will be frozen because you're not getting new entries in the table.
Oh, we assume after a moment,
So I'm saying you
we
generate
flush the table.
Okay.
When we reach some point, say, okay, there is no more activity on this interrupt, we flush the table.
when it's in a flush state, is it behaving like a menu then? What does it look like when
It's just not predicting any next interrupt for that source.
Yeah, so it's timer based,
your timer based?
yeah. Which would happen for menu as well. In updates.
So one more question. So when you have interrupt that you're recording every wake up, right? That might be one single interrupt, or that might be a set of 3 interrupts that arrive together, but because of the actual latch to your external wake up generator, you actually record only one while 3 came. And so do you have any means of what do you do in such cases? Do you just take one of them, because that might cause a different repetition of your periods?
So it's doing that per interrupt source, like as the source, an interrupt happens, okay? So this problem.
Okay.
All that matters is interrupt time. It doesn't actually matter how much work we do for the interrupt.
So in the embed governor that you tested, how did you take into account the IPIs? Do you have some kind of?
No, it's IPIs is just
You
put
don't
apart.
You don't care about them?
No, it's just for rescheduling. We don't take care about the other APIs. For the moment, I have to study, because I think there is a new API inserted recently. But basically, we don't take care about APIs. We assume it's part of the rescheduling.
On Pixel 3, it's not only CPU 0, it's also all the little CPUs.
Okay.
So
so
the
it's-
IRQ balancer uses the little ones for the device interrupt.
But who does the balance of the interrupt?
Is IRQ balance running as
Is doing that, yeah. So
because you mentioned only CPU 0.
yeah,
He was just saying parameterizing the extra cost.
Well, so.
5 minutes.
So I like this. I mean, as long as you get better results for the existing governors, it's all fine. The concern I have is that this is kind of a heavy, a fair amount of heavy computations.
Not so much actually, because I did the measurement on 86 x86 i7, and I had 1-2 microseconds to do the computation.
Well,
it's very fast.
So that's considerable, I would
What?
think. Yeah, because like you may basically so it is possible to have like one integer division in the governor, for in a simple case.
But we can fix all the idle code. We rip out all the stupid
Yeah.
divisions
We
and
got a lot of-
curly codes.
There's a lot of stuff we
The
can
manual
cut.
Yeah, so that's that too. But the manual governor has a lot of overhead, which is completely unnecessary in my view. But it's like, yeah, there is an amount of computation that you have to do, at least on the CPUs that get interrupts. And now that there are workloads in which there are very short idle periods, and then you
Yes.
get to you get to run something almost immediately. And in that case, it is the way, or is possible to avoid doing that.
Yes, that's exactly the point. I want to use the workload profile we have to say, okay, we are in this situation. We don't take care about. We have small duration. We don't take care about trying to predict anything because the duration are very small, and we have this very. We are loaded actually. We sleep a lot, but we are loaded. So we do the shortcut of going to choose the shallow state. But we need some kind of profile when we are to detect this situation.
I like this approach because I was planning to do something similar for the scheduler, since basically we take care mostly of the utilization, but we have no idea about the periodicity. Maybe we have a huge task that runs for 1 second and then sleeps for another second. The utilization is 0.5, and another task with the same utilization that runs for 1 millisecond and then sleeps for 1 second. This would be something that we still have for the energy. And I was wondering, does it make sense to get those results also offline for better managing the IRQ balancing, or directly reprogram the interrupt controller to put together similar interrupts with similar profiles, and maybe it would help to, like, that there's a class of interrupts that is very predictable. You put all the noise in the CPU 0,
Yeah.
and then maybe you can achieve better predictions on other cores.
What is possible is we have the feedback about the. We have the feedback about the. Well, in the governor we have a function called reflect, and when you enter this state, that happens when you exit. So you can do a check saying, okay, did that predict correctly or not? Is that what's correct, my prediction? You don't have to be very accurate, but say, okay, if I didn't break my target residency, and I still in what I was expecting, then you can say, okay, did a good prediction. And every time you do a good prediction, you can simply do a ratio between when you succeed and when you fail. And then from there, you can characterize your interrupt, saying, okay, that was it's periodic, and I always succeeded to predict when the periodicity on this interrupt because it's very stable. And say, okay, this one I can trust this interrupt. If you have other interrupt having a very bad performance, very bad score, saying no, you cannot predict anything on this one because it's very random, then in this case you can choose that. I think that's why.
I was referring to a next step, like once you have this data, maybe you can use it to find an optimal location of the different interrupts.
Yeah.
So
Okay.
which CPU is going to handle that interrupt? So maybe you have the CPU 0 who is never going to reach any deep idle state because it's taking all the noise. But other CPUs maybe can handle more predictable interrupts and are not going to do anything wrong.
I think it's not everything is possible from there. Yeah.
Probably extend the IRQ balancer, get feedbacks out of that, and reschedule interrupts and consolidate that.
The idea is good. You're pushing things to user space on IRQ buttons. No, I'm kidding. But there are also interrupts that you cannot move, like timer interrupts and the frequency of a scaling API. But the idea is.
But this can happen also at the different level. Maybe something that can
IRQ buttons.
We've definitely made changes on our end doing the reset API that were very, very beneficial in this case. Slightly different idea.
There are two classes of there are those that you can move, and there are those that you cannot avoid, like timers. There are per CPU interrupts.
For your socket,
Your idea is good for those that
do
you
you
can
admit,
move.
like, what about like when you have a spurious, do you have an edit distance?
Your idea is
No.
good.
So you're just doing this very stupid.
Yeah.
So it could probably be actually improve the game with like.
Yeah.
yes.
Okay.
And there are some improvements I recently had. For example, when you are looking for the period, you fall in the situation called overfitting.
Yeah.
That means when you have a smaller period, which is which are a subset. Well, for example, if you have if you go to 6 period, maximum 6, for example, and you find a period at 6, then you will never have a period of 3, because if you have 3 repeating, it's like you have 6 repeating. So you can reduce the loop by doing this iteration. Now there is the experiment show that maximum period I found for all the experiment I did for periodic pattern, it's 5. The maximum period is 5. So you just have to check 5, 4, and 3 period. 2 and 1 we don't have to take care, because if the period is 2, it's necessarily period 4 also, and if it's 1, it's obviously 5. So it's just 3 period. And there are a lot of small optimization we can do that to reduce the number of iteration.
I have just a question. If I got it well, the part where you apply exponentially moving average is done on a classified streams of interrupt delta times, which is done based on the delta times. So all starts from the delta times that are logarithmic. You take the logarithm and you put it in your bin.
Yes.
So the delta time is something that, as you have probably mixed sources of those interrupts, maybe you can get 2 periodicities that they overlap with each other, and let's say they affect each other in terms of, if one is really precise, happens periodically.
Yeah.
Then you would lose that, because in the delta times you always see
But
each period
the
of
EMA table is per interrupt.
Yeah.
It's per interrupt.
Per interrupt.
Yeah.
They are not mixed.
The EMA is just so you can go from a suffix entry to a predicted interval.
Yeah. Okay. Thanks.
If you didn't have the EMA and you just took like the midpoint or one of the extremes of the suffix interval, does it make a difference? Like how much did the EMA help?
Yeah.
Okay.
Okay. Thank you.